Hello everyone, this is Nithish Ravikkumar. Today I am presenting my project on news bias neutralization. We are all aware that bias in news media is a significant problem. So my project explores how we can use AI to detect that bias and rewrite text from a neutral point of view. So my project has three main objectives. The first is to detect the ideological bias which is present in the text which is given as the input. So I am exploring if I can use a modern transformer model, specifically BERT, to accurately detect the ideological bias. And the second objective is ground truth inference or to neutralize the bias. So once a bias sentence is identified, can the model automatically rewrite it? The goal is not to change facts but rather to remove the subjective and loaded language which is present and present the information from a neutral point of view. The third objective, which is also a major core contribution of my project, is the evaluation criteria. How do we even know if the rewritten sentence is correct? As we will see, the existing metrics are flawed. A major part of my work was to develop and implement new metrics, specifically a semantic similarity score and an aggregate bias score to properly measure the model's success. Now I will be going through the existing work in this topic. I reviewed the academic literature and I found a couple of papers which were relevant to this topic. From 2013, there are two papers by Hube and Fetahu and Recassens which focus on classification. Their models were designed to identify bias-inducing words and label full sentences as biased or non-biased. However, their key limitation was that they didn't fix the problem, they just identified the bias. Then I came across this paper by Prezant and their colleagues. This paper is titled Automatically Neutralizing Subjective Bias in Text. This paper tackled the generation task, actually rewriting the biased text. My project uses this paper, their data set and the model architecture as a starting point. Now for the motivation for doing this project. If this present paper already exists, then why even take up this project? My first motivation is the project itself. Subjective bias, like presenting opinions or facts using loaded language, is a pervasive problem which erodes public trust. So we need scalable tools to maintain a neutral point of view. This helps in both academic integrity and social order. The second motivation is to explore the gaps in the present paper. It's a fantastic paper, however, it has two main issues which I have spotted. One is the high computational cost. The models which were trained during this paper were on high-end hardware like NVIDIA Titan X GPUs, which is not readily available and is also expensive to access. So this makes it difficult for researchers or students to reproduce or build upon their work. The second limitation is flawed evaluation metrics. This is a critical gap. The paper's own automated metrics, which is BLUE and accuracy, they are poor measures of success. The authors themselves describe that there is a very weak association between BLUE and human evaluation scores. This is because if we rewrite the statement, for example, changing falsely claimed to stated, we will get 0% accuracy if the human reference text used described. It penalizes good paraphrasing. So my main contribution is to tackle both of these. First, by proving a low compute adaptation is possible, and second, by proposing new metrics which can actually measure the neutralization. Now will be moving on to the model architecture which I have used. This paper presented two architectures, the modular and the concurrent model. The modular model is a two-stage system. It has an explicit detector, which is basically a BERT classifier that finds the biased words, and there's an editor which is an LSTM with attention that rewrites them. The detector guides the editor using joint embeddings. The other model, which is the concurrent model, is a single end-to-end system that treats neutralization as a direct translation task from bias to neutral. In my project, I have adapted the modular model I chose this model for a critical reason. Its interpretable detector stage was essential for my self-defined metrics, evaluation metrics. So I couldn't have done this with the opaque concurrent model. At the same time, both of them share a very similar design block, which I will be explaining in the next slide. On the left, we have a BERT encoder, which takes the biased sentence and produces contextual embeddings. These are processed into hidden states for the decoder to attend to. The decoder on the right is an LSTM block that generates the neutralized statement one word at a time. It uses attention to look back at the encoder's hidden states, and the copy mechanisms help to copy important words such as names and dates. The key difference in the modular model I used is that there is an explicit detector step that gates this process, telling the detector which words to rewrite. Finally, both models are trained using token weighted loss, which I will be discussing further. This implementation slide covers the code implementation which I have used in this project. I built the project in PyTorch and trained it on Kaggle using the NVIDIA T4 GPUs. The total time which was required for fine-tuning the model was around 5.5 to 6 hours, which is more reasonable as compared to the computational demands as in the original paper. I structured the code into several files for clarity. The first file is the config file, which holds all the hyperparameters, which includes the model name, the LSTM hidden dimensions, and the alpha parameters. Okay, the second file is the data file, which handles all the data loading. It reads the TSV files like biased word train, which is a part of the original dataset which was included in the paper. I got it from the GitHub page of this paper. Also, I felt like the data in this dataset was not sufficient, and it did not include the specific targeted text which I was hoping for. So I generated a new synthetic dataset of biased neutral pairs to supplement the older Wikipedia data, which is the Wikipedia edit corpus which has been used in this paper. So this was generated using Gemini API, which I have included in this data file. So then this data file also contains functions which tokenize the source text for the BERT encoder and the target text for the LSTM decoder. I have already explained the model architecture earlier, and this model file contains the PyTorch class definitions for the modular models detector and the editor. The evaluation and the utility files contain the evaluation logic, which includes the standard metrics like token weighted loss, accuracy, and blue score. But I also implemented my own two metrics, which are the semantic score and the aggregate bias score, which I will be explaining in the further slides. This is followed by the train file, which is the main script which runs the entire process. It loads the config data in the model. It runs the main training loop using token weighted loss. After each epoch, it runs validation, and if the loss improves, it saves the model checkpoint, and finally it runs the full evaluation on the test set. Now moving on to the evaluation metrics. This brings back to the core problem which I identified in this paper, and it is one of my significant contributions in this project. The original paper's metrics are significantly flawed, at least as per my perspective. So if you look at accuracy, or which is exact match, this metric gives the model a point only if the generated token is identical to the human reference token. So this is a very strict criteria. If the model uses a particular word such as stated, and the reference text or the target text uses another word, for example described, then the model gets 0% accuracy, even though stated is actually perfect neutralization. It is equivalent, but still it is scored to be wrong. So this criteria, this metric is not very accurate, even though its name is accuracy. Now we look at blue score, which is slightly better. It measures the overlap of the word chunks, but it also suffers from the same problem. It penalizes paraphrasing. So it is designed for machine translation, where there is mostly just a single correct answer, but for our task there are multiple possible neutral rewrites. For that, we need measures which we need metrics which reward semantic correctness and not just exact string matching. So the solutions I have come up with are mainly two. The first is looking at semantic similarity score. So the goal is simple. I just need to measure if the core meaning was preserved after the first rewrite. So my score is actually a weighted average of two methods. 80% of the score comes from S-Bird similarity. I use a pre-trained S-Bird model to convert the original sentence and the new neutral sentence into embedding vectors. Then the cosine similarity of these two vectors is considered, and this gives us a deep contextual meaning. 20% of the score is from Jacquard similarity. This is a simpler metric which measures the overlap of content words. This acts as a sanity check to ensure that the key nouns and verbs are all intact and present. The final score, which is between 0 and 1, tells us how well we preserved the core facts, and the highest score is indicates a better performance. My second solution, or the second metric I came up with, is the aggregate bias score. This answers the other key question: did we really reduce the bias? This is also a composite score from 0 to 1, where 0 is neutral and 1 is biased. It works by averaging three factors: the P detector, the X lexicon, and 1 minus P neutral. These three factors are from the detectors models module. The P detector is the detector module's own opinion. I use the fine-tuned detector to get maximum bias probability for any word in that sentence. The second score, which is the S lexicon, is a compiled list of 14 academic subjectivity and bias lexicons. The score is based on the frequency of the words from these lexicons which appear in the sentence. The third probability factor is based on a ideological classification. Okay, I trained a separate ideological classifier, and the score is 1 minus the probability which I get from that, and the probability of the classifier thinking that the text is neutral is considered here. So by averaging these three signals, I can get a more robust and trustworthy score for bias. So my goal is to see that the score is high for the input text and low for the output text. Now I next after training and evaluating this model, I considered the performance and the result I have obtained through it. As I mentioned, I fine-tuned the pre-trained model from the cut. So next let's look at the performance and results. As I mentioned, I fine-tuned the pre-trained modular checkpoint. A key part of my method was using a hybrid dataset, which I mentioned earlier, using the Wikipedia corpus and my own synthetic dataset. The aim was to make the model more robust to certain and modern news topics. As we see in the table, which is here, my blue score was actually lower than the original papers, but this is not actually a failure because I expected this result. My new metrics will show that the model is actually generating valid neutral sentences, even though they do not exactly match the reference texts. Also, based on my own defined criteria, my model performs fairly well, and it actually exceeds expectations on specific types of data. This table summarizes the performance of my model against the original models, and as we can see here, the training strategy that I had adopted, which involves using the Kaggle, the GPUs available on Kaggle, are actually giving a result which is comparable to the original papers. However, there are certain issues with this as well. Cut. This table summarizes the performance of my model against the original papers. So you can see that my training strategy was more accessible than in the original paper, as I have been using a lower spec GPU and for lower time period. However, I have used a checkpoint model from the original paper, so that is also a reason for the lower training period, as I was just simply fine tuning the model. My exact match accuracy was 57.2%, which is lower than the original paper. But as we have established that these original metrics are not very accurate for predicting the model's performance or for identifying bias and neutralization. So according to my defined metrics, which are semantic similarity and the bias score, my model achieved a semantic similarity of 0.84, which is on the higher end. This shows that we have managed to preserve the core factual meaning of the sentences. One point I need to mention here is that the original paper also used a similar measure which is called fluency. However, this was not an automated measure. It was done by human observers who rated the output against their own reference outputs. This was highly subjective and based on the human's experience and self-bias. So this measure cannot be considered to be a true measure of the model's performance. So we have achieved a massive measurable drop in bias while maintaining a high degree of semantic meaning. This demonstrates that the model's success is actually better than what BLEU or accuracy could actually predict. So this wraps up my project. Now, if we talk about the scope for improvement in this project, I think this was a successful proof of concept, particularly for the metrics which I have used here. However, there is a clear path for future improvement, mainly in 4 areas. One is to modernize the decoder. The LSTM decoder I have used is actually on the older side. This paper came out in 2020 and there have been progress made since. We could use a modern transformer decoder, which would most probably boost performance. The second change we could do, or the second improvement, is domain adaptation through web scraping. There are a lot of news articles on the internet and we could scrape thousands of them and continue pre-training BERT on them. This would adapt the encoder to specific vocabulary and the syntax of news media, making it more effective. The third method is to refine the synthetic data. My use of LLM to generate large amount of data was a good start, but this can be expanded to create a much larger and more diverse data set. The fourth method is to integrate fact checking. A key limitation is that this model does not look at the truth behind the statement itself. A future version should integrate a fact checking module to verify the output against the original source text. These include the reference materials, the key papers and data sets I had used in my project. Now I would like to demonstrate a working example of my project. So I built the front end of my project using Streamlit, and now I will be pasting as a random excerpt of a statement. And here I have got 3 options. I can look for bias classification, neutralization, or bias score. I can choose any and all of them. So for this example, I will be choosing bias neutralization and bias classification. So let's look at the result. Since the model is running locally on my laptop's GPU, which is limited, the execution takes some time. So the result shows that the input was neutral in bias, and it was the rewritten statement is fairly similar to the input statement. Now I will be running another example through this model, and I will also be looking at that output. This input is shown to be left leaning, and the model has given the output, which is said to be the neutralized text. This can be downloaded in txt format. Also, if I want to look at the bias score and similarity, I can choose the appropriate option from the dialog box, from the sidebar. So in this situation, since I have not chosen bias neutralization checkbox, I only get the bias score and the classification. So the bias score is set to be 38, which means that the bias is not very high, and and the semantic similarity of the neutralized score which was obtained is 82%. So it shows that the resultant text is fairly similar to the original text, and the bias has been highly neutralized. So this concludes my presentation. Thank you.